Welcome back to STEM Online Academy. My name is Jason Masterakos for those of you who don't know me. And also, what is this channel about? Our channel is a channel on applied mathematics and physics for the undergraduate student who wants to get ahead, wants to challenge themselves, learn interesting concepts, and also improve on their exams or any other tests that is required of them. Okay. So, what we're going to focus on today is something interesting, and it's something that a lot of people have, some misconceptions on. And I thought I'd divert to this today, which is very important. Uh, we're going to be looking at something called L'Hôpital's rule. Okay, so we're going to discuss that. Hopefully, you know what L'Hôpital's rule is. If you're not familiar, I'm going to remind you what L'Hôpital's rule is. Okay, all right. So we're going to be discussing this today, and we're going to look specifically at why this limit looks deceptively easy. Okay, there's going to be an example below that's going to be talking about a limit that looks like it needs to use L'Hôpital's rule, but it's actually a trap. We're going to talk about the L'Hôpital's reflex, number 2. 3, local behavior near 0. Okay. Number 4 is going to be series structure and small angle approximation. Okay. And number 5 is going to be an application on waves and oscillations uh, in uh, in the specific limit, pretty much. Not the specific limit, but in general, um, how this type of function can be applied in physics and etc. Okay, so let's get to it. All right. So what we're going to be looking at is we're going to be evaluating the following limit here. Okay, we want to evaluate this guy. We want to evaluate the limit as x approaches 0 of sine x minus x all over x cubed. Okay. Now, there's a reason why I want to bring this up because there's common misconceptions of when to use L'Hôpital's rule and when you can't use it, sort of, and etc. Right? Okay. Let me remind you what the definition is. Okay. So L'Hôpital's rule, for those of you who don't know, right? Right. So I'm going to put over here probably. Might put it over here. Yeah, let's put it on the side here. So for this solution, right? L'Hôpital's rule states the following. Okay. Let me just put here. I'm just going to remind you of a definition that's important. So definition of L'Hôpital. Okay. Definition of L'Hôpital. L'Hôpital. L'Hôpital says the following, right? Is that if you take, so if you have, so given a function, right? So given, second, given a function, say the function is called f of x, okay? And another function g of x, okay? And another function function g of x. Okay, so g of x would be called g of x. And you find the ratio. Okay, and you take and you take their ratios, right? And you take their ratios and you take the limit, right? The limit of their ratios, okay? Their ratios as follows. Let's go to the next page. Then what ends up happening is, I'm just going to say continuation here. So continuation, continuation. continuation. Just going to put an arrow here, just saying that continuing. You get the limit as x approaches a of f of x divided by g of x. Okay, any limits in this form is equivalent to the limit as x approaches a of f prime of x over g prime of x, provided that g of x cannot equal to 0. Okay, so g of x cannot equal to 0. Okay, make sure that you drill this in. Okay, you need to make sure that you drill this in. G prime of x cannot equal to 0. Okay, in other words, you can use L'Hopital's rule as long as you have a limit. You're taking the limit as x approaches some number a of some function divided by another function, provided that the function at the bottom cannot equal to 0. Okay, and it doesn't, when you take the derivative of the limit in the denominator, doesn't give us indeterminate form, right? Indeterminate form means anything of the form. So you want to make sure anytime when you're taking the limit of two functions, one divided by another, okay, you want to make sure that what's in the denominator doesn't go to 0. Otherwise, you can't evaluate the limit. Okay. So what do I mean by that? If you look at our example, sine x minus x over x cubed, if I were to plug in right away x goes to 0, I get 0 in the denominator. That's indeterminate. I can't allow that to happen. Okay. Right. Just going to put a note here. So note. I may say important in red. Important. Okay. Use L'Hopital's rule, right? So use L'Hopital's rule. L'Hopital's rule in order to avoid any of the following. All the following, to say all of the following. Okay, and the following is this. If you have things like, put here, 0 over 0, right? 0 over 0, infinity divided by infinity, infinity divided by 0, and let's say, yeah, that's pretty much it, right? These types of cases, indeterminacy, okay? Now, for this problem that we're doing right here, if we plug in x is 0 in the bottom, right, we get it indeterminate. So we need to use well, we would think that we'd have to use L'Hopital's rule, okay? And the reason why L'Hopital's rule actually doesn't work here, right? Let's test it out, okay? Let's look at the problem, okay? So looking at the problem, solution to the problem, right? So the solution, I'm going to go step by step here. So pay attention to each step, okay? So if you look at the limit as x goes to 0 of sine x minus x divided by x cubed, okay? If I take x goes to 0 here, right, it's indeterminate. So we want to apply L'Hopital's rule. But here's the problem. If I do L'Hopital's rule as x goes to 0, right, I have to take the derivative of the numerator, right? So take sine x minus x prime all over x cubed prime. Take the derivatives with respect to the numerator and the denominator, okay? Now, here's the thing. If I were to do that, I get the limit as x goes to 0 of the derivative of the numerator. Sine x becomes cosine x. Minus x becomes 1. X cubed becomes 3x squared. However, though, if I were to now put in x goes to 0, what would happen in the denominator, numerator and denominator? What do you think will happen? Well, it's indeterminate. right? What we were trying to avoid with L'Hopital's rule is make sure it's not indeterminate, but we're getting indeterminate form because we're getting a number, right? Because if we were to do this, cos 0 is 1. Okay, so cos 0 is 1, 1 minus 1 all over 0, right? This gives us 0 over 0. That's a problematic situation. So we need to avoid using L'Hopital's rule in this case. Most people would fall for it. Okay, so don't do that. You have to make sure when you're doing L'Hopital's rule that what you're trying to avoid is another indeterminate form, right? Okay, you want to make sure you avoid that. Otherwise, you have a problem. Okay, so we have to find another way to solve this. So another way to solve this, right, is to do the following, right? Take the limit as x goes to 0. See, before I solve, I want to show you something that might give you an insight, a geometric insight on how to approach this. Okay, so let's look at a simulation. Okay, let's look at a simulation here. I made a simulation earlier, so pay attention. We're looking at the limit. The model says, right? Right. So here's the model. Just 1 second. Okay, so rewind here. The model says that we have a limit as x approaches 0 of sine x minus x all over x cubed. And what we should be getting is a horizontal asymptotal line of y equals -1, 6. That's what this limit should give us, okay? So first off, by making a geometric model or a mathematical model of some sort, it can tell us the behavior of what's happening and what we should be expecting to solve when we do it algebraically, right? So our solutions to give us -1, 6, okay? But another thing about the graph that is important, right, is that that horizontal line there, y equals -1, 6. Okay, so pay attention, right? So you see that point P there, that dot is moving horizontally. Okay, that's going to cover the whole thing, right? So our limit is -1, 6. Another thing too, we can see that we should have some sort of series near x equals 0. Okay, so I'm saying about x equals 0, something's going to blow up. Okay, so around x equals 0, this is giving us some intuition on how to solve this, okay? So pay attention at x equals 0, right? We should have some sort of series solution to solving this limit, okay? So sine x would be approximately equal to x minus x cubed over 6, plus, higher powers. Right? That's what our model is telling us, okay? It's going to make more sense, right, when I do it uh, algebraically, okay, as opposed to showing you just the simulation. Okay, but the simulation can provide hints on how to solve the problem. Okay, so as you can see again, right, the series intuition near x equals 0. Okay, we have sine x approximately equal to x minus x cubed over 6 plus dot 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 dot. Right. By the way, that's telling us that we may have to substitute some sort of series into our function, the sine x part, anyways. Okay. Right? And what we should expect is our final result to be -1, 6, or candidate limit that's called here, okay? All right, so you want to make sure that our series, right? We're going to provide a series intuition near x equals 0, okay? All that's saying is that we have some sort of a power series, to be more precise, right? About x equals 0, right? Right, because it's intuition of x near x equals 0. Okay, so let's go look at that. Back to the desktop. All right, so let's look at it right now. So we're going to do a substitution. Okay, so limit as x approaches 0, sine x. This is a power series substitution. Okay, so this means that this is going to be equivalent to the sum from n equals 0 to infinity, okay, of -1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. This, if you're not familiar with this is just the power or Maclaurin series of sine x, okay? Right? That's what this is. So that's why I substitute into sine x, right? Minus x all over x cubed. If you don't, you should know that in your calculus 1 classes. You should have been taught what a Maclaurin series is, right? And that sine x, cos x, tan x all have Maclaurin expansions. Okay, so I'm just saying here by substitution, I'm saying by using, I'm going to put it here, it's good to have a justification of where that equation came from. Always put justifications for every step. Otherwise, mathematically, you don't have justification to put it in, okay? So this, I'm going to say this is definition. This is by definition, right, of a power series expansion of sine x, right? Of sine x, which we said here, sine x is just this, right? N equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, I'm going to make it better here, 2n plus 1 divided by 2n plus 1 all factorial. Okay, that's what I'm using here. Okay, hope that makes sense. All right, now what we need to do here is we can expand this out. Okay, this actually, if we plug in starting at n equals 0 here, right? So when n is 0, well, we get something interesting. The first output, right? What's the first output? First output is going to be x, right? So it'd be x. Okay. The next one, when n is 1, remember we increment 1 when we have a summation. So when n is 1, 2 and 1 gives us 3, x cubed, negative 1 to the 3. So that's negative 1 all cubed gives us negative 1 times x cubed. So this becomes negative x cubed all over. Remember, 1's down here, so that's 3 factorial. 2 plus 1 is 3 factorial. So negative x cubed all over 3 factorial. The next one should be, what, want to guess the next one? Try it yourself, and I'll put it in. Now we're looking at n equals 2, so substitute it into this summation above, right? It should be something interesting. Plus x to the 5, okay, over 5 factorial. So I just substituted what the sine x part was, okay? This part here. And then minus x all over x cubed. Okay, right, so we got that. Then it's going to be, now we just need to clean this up. Limit as x goes to 0. Okay. Yeah, we can do this right now. So first off, what you're going to notice is that our x's will cancel. By the way, I should have, I mean, it's like a mistake. To be accurate, if you want to continue going to all high powers, this is a Maclaurin series, so this is an infinite series, so I can actually say minus dot dot dot, depending where I want to stop. I'm going to stop here, okay, up to the 5 or whatever, x to the 5 over 5 factorial, so it's specified. Now over here, now what you're going to notice, okay, is that like terms, x's are gone. I'm left with minus x cubed 3 factorial plus x to the 5 over 5 factorial. This is a minus, by the way, minus, okay, all over that x cubed. Remember, I'm dividing everything by x cubed, be careful, okay. Next step is to look at the limit as x goes to 0, okay. If I'm dividing by 3, this gets canceled, I'm left with negative 1 over 3 factorial, okay. That's a factorial. Then x cubed divided by x to the 5th gives x squared plus x squared divided by 5 factorial. Okay, 5 factorial here. And then over here now we have the limit as x goes to 0 Okay, just using a different color. I think that makes it more interesting. Take the limit of each side, everything inside, right? So you're going to go in here and then you go over here. Okay, so limit of the blue part here now will be negative limit of 1 over 3 factorial plus limit as x goes to 0 of x squared all over 5 factorial. Okay. All right, so then from here now we have negative 1 over 3 factorial. I'm taking the limit of this guy. I can move limit as x goes to 0. I like to solve my steps. You probably can do this in one bang if you want, right? Doesn't matter. So 1 over 5 factorial. 1 over 5 factorial. Bring the constants from the limit. This limit as x goes to 0. 1 here. Now, automatically, sorry about that. This would be x squared. Since x is going to 0, this is gone. I'm just left with this. Limit of a constant is a constant times negative 1/3, negative 1 over 3 factorial, so negative 1 over 3 factorial. 3 factorial is 6. So this gives us negative 1 over 6. And if you were paying attention, this is the exact answer that we got for our limit in the simulation. Okay. So I hope that was a good explanation of why um, you want to be careful using L'Hopital's rule. Just because you have a function divided by another function of a limit doesn't mean necessarily you can use it, especially if what you're trying to avoid is an indeterminate form and it produces another indeterminate form, you have a problem. Okay. All right. So another thing, I want to show you a physical interpretation of this. Let me get to that. Now, we're looking at application in physics. Now, what I did here to solve this problem, I used a Maclaurin, as I said, a Maclaurin series for sine x. Okay, that's this guy here. Okay, and the expansion gave us x minus x cubed over 3 factorial and so forth, plus x to the 5th or 5 factorial, da, 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 da. Now, it turns out this can also be dumbed down to something called a small angle approximation, which I'm going to talk about in part 4 and part 5 really quickly here, right? Small angle approximation. Okay, the small angle approximation for sine x is x. Okay, so sine x is always x. All right, so I'm going to put over here sine x is always x. So small angle, right? So I'm going to put over here small angle. So I use small angle approximation to solve this. That problem there actually. Well, part of it, it's embedded in the Maclaurin expansive sine x. Small angle approximation. My small angle approximation, the definition. So the definition is that x is approximately equal to sine x. Okay, cos x it's something different, but for x it's really handy to use sine x. Now I want to show you how it's not. I'm not going to go into in detail, but it has applications in physics actually. Okay. Yes, very interesting applications actually. So the application, one of the applications in wave, when it comes to oscillations, like simple harmonic motion, if you take in physics classes, and or waves. Okay, that's where this definition, small angle approximation, is used. All right. Now the small angle approximation, okay, can help us with pendulums. Pendulums undergo something called simple harmonic motion, which means that it's periodic. They always go back to the same equilibrium type of phase points. Okay, so let's say I have a ball, yellow ball down here. I labeled it M. Okay, and I have a ceiling up here. Okay, this part here is my ceiling, and that ceiling has some, is tied to some rope, right? And that rope has some length L, so length L. the length of the rope. Angle theta is the angle from, you know, the length of the rope to the vertical there. That's my angle theta. Okay, this guy here, right? So we have theta, we have L, we have M, right? And the mass of the ball. Now, the mass of the ball is hung taut, right? It's been displaced. Okay, it's been displaced. That's why we have that angle theta. If the line L or the rope L was perfectly vertical, we wouldn't have an angle. But since I've displaced it, right, I've moved my ball with mass M away from the vertical. Okay, that's why there's that angle uh, angle of that vertical angle, right there, angle theta. Okay, so mass M is there. Now, since there's a mass M, some common sense, even if you don't know physics. What does mass M go? Weight. And that weight we call Fg or mg. Okay, mass times gravitational acceleration. Now, what ends up happening is that you can actually have, when you're dealing with problems like this, you will have XY components. Right? Anytime when you have angle thetas involved in uh, free body diagrams in physics, you want to decompose it into XY. I'm getting very technical here. It's supposed to be mainly a math video, but I'm showing you the application as well, the applied mathematics side, right? And the XY direction can be a slanted XY direction, but you always have to define your XY direction. So positive X, positive Y, okay? Because there's actually an X. I'm going to put over here, there's an FGX. There's an F. This is your FGX component of the gravitational force, okay? And an FGY, okay? And FGY over here. Sometimes you call it an F perpendicular or F parallel, okay? And it turns out when solving pendulums, we use the small angle approximation. So I'm trying to show you the link between how we solve L'Hopital's rule using a subset of the Maclaurin expansion, which is the small angle approximation, and then showing you that that same small angle approximation could be used to solve interesting, uh, you know, simple harmonic motion problems, right? So for instance, something like this, okay? So I thought that would be cool. I'm not going to do this problem, it gets pretty technical. But if you're looking for resources, you can always ask me for it. And that's what brings me to the end of this video, okay? So if you enjoy, um, if you enjoy thinking or thinking like this, or want to get, uh, or you have trouble with, you know, calculus, ODEs, or differential equations, or your physics courses, uh, and you really need help, you can always contact me. I'm a coach slash tutor when it comes to this. Always contact me at www.stem1online.com. It will be in the description below, okay, at the end of this YouTube video. And or if you're looking to solve interesting calculus problems, now they're mainly integration problems. This was a linear problem, mainly integration problems. And either you want to build, and you have a foundation in integral calculus and linear algebra, and you want to build your mathematical toolkit with hard problems, or it's a mixture of starts off easy for those of you who want to just continue building your knowledge. Okay, so number one, and or you're looking for hard problems in general to solve. There's a section on that. Then you're in luck, right? Advanced Integration Techniques, my book, is the perfect calculus methods book that can help you really accelerate in your undergraduate endeavors. All right. All right. So, and also there will be a link to that too if you're looking for references to learn more. Okay, when it comes to calculus. All right. Okay, so that is it for today's video. I hope you enjoyed it. Again, Wednesdays are the live shows. I may not do one this Wednesday. It may alternate to something else because I'm a bit busy, but we'll see. But it's Wednesdays, 8:30 p.m. Eastern is the live shows. Sunday is a stream, regular stream, and Thursdays is a stream as well. Have a good night, guys. I'll see you next time. Don't forget to like and subscribe. Like, please like and subscribe. Bye bye.